Hello students, I welcome you all to the session on power supply. This topic is included in third semester of BSc as prescribed by Karnataka University Dharwad. The learning objectives of this session are to know about the power supplies and the different types of power supplies, to know about the rectifiers and different types of rectifiers, to understand peak inverse voltage, ripple factor, and the rectifier efficiency. Session outcomes are explain the working of power supplies, explain the working of rectifiers and different types of rectifiers, get an idea about peak inverse voltage, rectifier efficiency, and ripple factor. So let us start with the power supply. What power supply is? So, a power supply is a device which converts AC voltage into DC voltage. It is a combination of a rectifier circuit, a filter circuit, and a voltage regulator circuit. So, all three together, combined together, that is a rectifier, a filter, and a voltage regulator together, is called as a power supply. There are two types of power supplies: unregulated power supply and regulated power supply. So let us know what unregulated power supply is. It is the power supply whose DC terminal voltage changes significantly when its input load varies. So if the resistance in the circuit varies, the input resistance in the circuit varies, it is observed that the DC terminal voltage, that is the output voltage, changes significantly. So such a power supply wherein the output voltage is fluctuating is what we call it as unregulated power supply. As load draws more current, the terminal voltage becomes less. Here, the DC voltage doesn't remain constant due to the variation in the load current, main voltage, and the ambient temperature. So these are the factors on which the DC voltage depends. So if the output DC voltage is not constant with the variations in the load current, the main voltage, and the ambient temperature, then such a power supply we call it as an unregulated power supply. Now let us know what regulated power supply is. So regulated power supply is a power supply whose terminal voltage remains constant irrespective of the change in the AC supply or load. So even if the input load varies, there will be no change in the terminal output voltage. So that's why it is called as a regulated power supply. Regulated power supply is actually the combination of unregulated power supply and a voltage regulator. So an unregulated power supply can be converted into a regulated power supply just by connecting a voltage regulator circuit in front of it. An unregulated power supply can be converted to a regulated power supply by applying a voltage regulator to it. This is the block diagram of the regulated power supply. So in the block diagram, you can see there are certain circuits which are kept one after the another, and the whole together is considered to be the regulated power supply. So here at the input, you have connected it to the AC supply, which gives 220 volt input. So here the waveform is shown. You can see the peak voltages which are varying from positive terminal to the negative, plus Vm to minus Vm. It is connected to the transformer. What transformer does is it either steps down the voltage or it step ups the voltage. So here usually we use a step down transformer. So here the voltage is decreased. The output of the transformer is having lesser value of Vm, the peak voltage, as compared to the input. So the step down voltage is going to be fed to the rectifier. Now here the rectifier is going to convert this AC voltage into a DC voltage. Here usually we use a full wave rectifier. So you can see the output of the rectifier has both the cycles of the waves, that is the positive half cycle as well as the negative half cycle, which is being shown here at the output of the rectifier, but both the half cycles are in the same direction. Okay, so this output is fed to the filter. What filter does is it removes the ripples from this output of a rectifier. So the function of the filter is to smoothen the output of the rectifier and to make it completely into a DC output. So filter output, you can see here, it is not that smoother as you have considered, but still there are certain ripples that are present in the output of the filter, which is again fed to the regulator, which regulates the voltage. The minor ripples which are remaining in the output of the filter is regulated by the regulator circuit, and the output of the regulator can be seen to be much more smoother, a straight line, much pure DC output, you can say. That pure DC output is fed to the load. So this is how the power supply, regulated power supply works. Now let us come to the rectifier circuit, which is a very important part of the power supply. So what a rectifier is? Actually, it is a circuit which employs one or more diodes to convert an AC voltage into the pulsating DC voltage. So a circuit which converts AC to DC, we call it as a rectifier. There are actually two types of rectifiers. One is full wave rectifier and the second one is half wave rectifier. The half wave rectifier actually only rectifies the half wave of the input. So it is as shown in the figure below. You can see the figure of the half wave rectifier here. The AC voltage is applied to the single diode connected in series with the load resistor. So here in the diagram you can see the input AC is connected to the primary of the transformer. The input AC voltage is stepped down by this transformer, and the transformer, one of the terminals of the transformer is connected to the diode, which in turn is connected to the load resistor across it. So here the input waveform is shown below. You can see both the waves, that is the positive half cycle as well as the negative half cycle of the wave here. This is fed to the diode. So during the positive half cycle, it is seen that the upper part of the secondary becomes positive and the lower end of the secondary is negative. So because the upper end of the secondary is positive, diode becomes forward bias and the diode is going to conduct the current. So the current I flows through the diode and it flows through the resistor. And that's why at the output, that is AB, at output terminals, you are going to get the positive half cycle, which is shown here at the output waveform. So output waveform, you can see the positive half cycle is coming out. During the negative half cycle, what happens is the upper end of the secondary becomes negative and the lower end of the secondary becomes positive. Because the upper end is connected to the diode becomes reversed bias, and because the diode is reversed bias, it is not going to conduct the current. So because diode doesn't conduct the current, there is no current flowing through the load resistor R, and that is why there is no output seen at the terminals, the output terminals. So that's why the negative half cycle is totally eliminated. Again, during the next positive half cycle, what happens is, again the upper end of the secondary becomes positive and the lower end of the secondary becomes negative. That's why the diode again becomes forward bias, and again the diode is going to conduct the current flows through the load resistor, and at the output you will get the output voltage. So here you will be getting the positive half cycle again, and this continues for every cycle. For every cycle, positive cycle is coming out, but negative cycle is totally eliminated. So in this way you will be having only half cycles that are occurring at the output, and because you have only half cycles occurring at the output, it is called as a half wave rectifier. So you can understand why it is called as a half wave rectifier. So here during the positive half cycle of the input AC, I told you that diode is forward biased and it conducts. So hence the current flows through the load resistor RL. But during the negative half cycle, the diode is reversed bias and it does not conduct. So there will be no current that is flowing through the load resistance RL. Since only one half cycle of the input wave is used, it is called as a half wave rectifier, and at the output you will have only a half wave coming out. So what is a full wave rectifier? Let us see how it is designed and how it works. The full wave rectifier circuit is shown in the diagram below. Here it consists of two diodes, diode D1 and diode D2. You can see the circuit diagram is a little bit modified. Here both the diodes are in turn connected to the load resistance RL, which in turn is connected to the central tapping of the secondary at the point C. So here what happens is, when you apply the input to the primary, the secondary is going to give the step down voltage. Here at the point A, during the positive half cycle, the terminal point A, or you can say the upper end of the secondary, becomes positive and lower end of the secondary B becomes negative. Upper end A is positive, so that's why diode D1 is forward bias. So diode D1 is going to conduct the current. So now the current is going to flow through diode D1, then it flows through load resistance RL, and it is going to the point C here. Okay, so this circuit is completed. Here the current flows through the diode D1, load resistance RL, and back to C. But at the same time, you can see the point B, that is the lower end of the secondary, is negative. And because the lower end is negative, diode D2 is becoming reversed bias. Diode D2, which is reversed bias, is not going to conduct the current, and that's why no current flows in this direction now. Okay, so during the positive half cycle, diode D1 has conducted, and you have the voltage across the load resistance RL, which is shown by the waveform here below the circuit diagram. So the positive half cycle is occurring here. Okay, what happens during the negative half cycle? During the negative half cycle, you can see now A becomes negative and B becomes positive. Now A is negative, so that's why diode D1 is going to be reversed bias. So it is not going to conduct the current. So there will be no current flowing in the upper half of this circuit. So diode D1 is not conducting in this condition. But at the same time, if you see the lower diode D2, here because B is positive, diode D2 is going to be forward biased, and the current is going to flow through D2, then through load resistance RL, and then it is going to move to the point C. So here during the negative half cycle, diode D2 is going to conduct and the current is going to flow through RL, and voltage appears across RL. That voltage is shown here in the waveform. That is, even during the negative half cycle, you can see in the same direction the current flows in load resistance RL. So in which direction the current has flown through the resistance RL during the positive half cycle, during the negative half cycle also the same direction is followed, and because of that you will be having both the halves in the same direction. That is, you will be having only positive half cycles here. Okay, so here you can see all the full wave has been rectified. The full wave is appearing at the output, and because it is the full wave that is appearing at the output, it is called as a full wave rectifier. So here I have given the working. So what I have told now, that is itself being repeated again. So during the positive half cycle of the input AC signal, end A becomes positive and end B becomes negative. That is why diode D1 is forward bias and it conducts, whereas diode D2 is reverse bias and it does not conduct. So current flows through the load resistance RL, producing the output voltage. During the negative half cycle of the input AC signal, end A becomes negative and end B becomes positive. And because of that, now diode D1 is reverse bias and does not conduct, whereas diode D2 is forward bias and it conducts the current. Again, the current flows through the load resistance RL, producing output voltage. Thus, during both the half cycles, current flows through the load resistance and the voltage is developed across the load during the entire cycle, and that is why it is considered to be the full wave rectifier. There is one more rectifier which is also a full wave rectifier, that we call it as bridge rectifier. The bridge rectifier is a rectifier which consists of 4 diodes which are arranged in the form of a Wheatstone's network. You can see the diagram here which I have shown below. So here what happens, during the positive half cycle of AC, point A, you can see the Wheatstone's network, the top node of the Wheatstone's network, that is point A, becomes positive, whereas the very opposite node, point C, becomes negative. Because point A is positive, here you can see diode D1 becomes forward bias. Okay, but the current can't flow through D4. So current flows through D1, but because D4 is reverse bias, so there will be no current flowing in that direction. So now the current flows from A to B. Again from B it is not going to flow to D3 because it is again reverse bias here. So the current flows from B to B towards the load resistance. Through the load resistance it comes back, it comes to the point D. Now at the point D again there are 2 diodes, diode D4 and diode D2, but diode D2 is forward bias. So the current flows through diode D2 and it comes to the input again back. Okay, so in this way, during the positive half cycle, the current flows from point A through the diode D1 to point B, then through the load resistance, it comes to point D. From D, it goes to diode D2, it comes at point C, and from point C, it comes back to the input of that rectifier. Okay, so now during the negative half cycle, let us see what happens during the negative half cycle. So during the negative half cycle, now A becomes negative and C becomes positive. Now because C is positive now, the current is going to come to the point C, and from point C, current flows through D3 because D3 is forward bias, but at the same time D2 is reverse bias. So the current flows through D3, then it comes to point B, and again here there are 2 paths for the current. It can move towards D1 or it can move towards the load resistance, but D1 is reverse bias, so it will not go to D1, but it will move from B to load resistance, and from load resistance it comes back to the point D, and from point D, here you can see D4 is forward bias now, so it moves towards D4 and the current flows through D4 to point A and from point A to the input. So in this way the current flows in steps. That is, during the positive half cycle, you can see diode D1 and D2 are forward bias and they conduct. So across the load resistance you will be having the current flowing through. So at the output terminals you will get the voltage. So during positive half cycle you will be having the two diodes D1 and D2 forward biased and conducting, so output is observed across the load. Similarly, during the negative half cycle, diode D3 and D4 conduct, and again you will get the voltage at the output. So in this way we get the full wave at the output, and because the full wave is rectified and obtained at the output, we call it as a full wave rectifier, or the other name is bridge rectifier because its construction consists of a Wheatstone's bridge. Okay, so here both the cycles, that is positive half cycle as well as negative half cycle, is obtained at the output, and because of that it is also called as a full wave rectifier. Now let us come to the peak inverse voltage. What is peak inverse voltage? Peak inverse voltage is the maximum possible voltage across a diode when it is reverse bias. So whenever the diode is reverse bias, it is not going to conduct the current. So whatever voltage is obtained across the diode during the reverse biasing is what we call it as peak inverse voltage. For the half wave rectifier, because we have only one diode there, the peak inverse voltage is Vm. So whatever voltage you have applied at the input, all is going to be obtained across the diode during the reverse biasing case. So here peak inverse voltage is Vm for the half wave rectifier. For the full wave rectifier you have two diodes, so the peak inverse voltage is 2 Vm, and for the bridge rectifier it is Vm. Let us move further to rectifier efficiency. So what is rectifier efficiency? It is the ratio of output DC power to the total input power supplied to the circuit. So the DC power that you are going to get at the output, if you take the ratio to its input power that is being supplied, then that ratio is what we call it as rectifier efficiency. Rectifier efficiency is always mentioned in percentage, so that's why you are going to multiply it by 100. The efficiency of a half wave rectifier is 40.6%, because you can see only half wave at the output, so the power is almost half there, so that's why you will be getting the efficiency as 40.6%, whereas efficiency of full wave rectifier is 81.2%. Similarly, the efficiency of the bridge rectifier is 81.2%. Let us see about ripple factor. So what ripple factor is? It is a ratio of RMS value of AC component to DC component in the rectifier output. So if you take the ratio of RMS value of AC component to DC component, then we call it as a ripple factor of the given rectifier. So the ripple factor of the half wave rectifier is 1.21, which indicates that AC component present in the output is 121% of the DC voltage. Therefore, half wave rectifier is a poor converter of AC into DC. For a full wave rectifier, the ripple factor is 0.482, which is much smaller as compared to that of a half wave rectifier. Hence, the full wave rectifier is preferred to a half wave rectifier. For a bridge rectifier also, the ripple factor is 0.482. So with this, we have come to the end of this session. So we have certain multiple choice questions based on this session. So let us just go through them. So in an unregulated power supply, if the load current increases, the output voltage, so the four options are remains the same, decreases, increases, none of the above. Because it is an unregulated power supply and the load current is increasing, means the output voltage is going to decrease. Okay. Second question is, power supply is a combination of. So power supply is a combination of which circuits? So rectifier, filter, voltage regulator, rectifier and voltage regulator. The third option is filter and voltage regulator. Fourth option is none of the above. So the correct option is option 1, that is rectifier, filter and voltage regulator. Question 3. Ripple factor of the full wave rectifier is 1, 0.48, 1.21 and 2. So just now we have studied about the ripple factor, and you have studied for the full wave rectifier the ripple factor is 0.48. So option 2 is the correct option. Next question. The ratio of RMS value of AC component to DC component in the rectifier output is known as ripple factor. Second option is rectifier efficiency. Third, peak inverse voltage. The fourth option, none of the above. So the correct option is ripple factor. Next question. The efficiency of half wave rectifier is 42%. If the applied AC input power is 92 watt, find the DC output power. So here the efficiency is given and the input power applied is given. What you have to find out is output power. So the four options are given: 50.76 watt, 92 watt, 38.64 watt and none of the above. If you solve this for the efficiency formula by putting the efficiency formula, because you know the efficiency formula is nothing but it is the DC output to the AC input power. Okay, so if you just put it, you will get 38.64 watt. Okay, so this is all regarding the session for today. I thank you all for the patient listening. Thank you.